I'm very honored to be here. My name is Shinichi Satoh from National Institute of Informatics, Tokyo, Japan. Today I'd like to talk about a couple of our research projects and under the title of Indexing Video Archives Using Latent Link Analysis. Let me first start by the motivation of our research projects. First of all, we regard broadcast video is okay. Right. So, well, broadcast video, as you may know, is very rich and high quality information source. And recent environment enables us to access huge broadcast video archive. One example would be, can I use this? Maybe. One example is NHK archives. You know NHK? NHK is a Japanese broadcast company, but this is world's second largest broadcast company. And it maintains huge video archives, and we can have access if we visit this specific building, or they open the archive to public using video on demand service. So they have several 10,000 hours of video archives in there. And also BBC. So you know BBC. So BBC is the world's largest broadcast company. This is the first, this is second. And they also maintain huge video archive, and they have TV on demand service as well. And in France, of course you may know, you have INA, Institut National de Audiovisual, and they have huge video archives as well of French TV programs. And they serve that to researchers as well as for commercial purpose as well. And yet another direction. Recently, Toshiba Corporation, which is Japanese TV set production company, they started to sell new TV station, which is called Cell Rexa. This is a flat panel TV. Not only that, it is equipped with 3 terabytes of disk. Do you understand that? It has disk array attached to this TV station, and it can record large amount of TV programs. And you can even browse or search TV programs, as you can see. So if you start the search of TV program, you can see this screen. And at the center, you will have one program and related TV program according to genre or characters or keywords. You can see many related TV programs, and you can browse. So, as such, based on those kind of environmental change, we can have huge amount of broadcast video archive. However, to effectively utilize such kind of information, of course, we need search function or knowledge discovery from that kind of TV video archive. Once we achieve that, of course, that should be very beneficial for daily life support, such as education, study on politics or economy, culture, marketing analysis, etc., etc. So, key point is image or video search, of course. If we think about current state-of-the-art image video search, of course, most TV image video search function is based on text. Maybe you know. For instance, YouTube, Flickr, Google Image, everything is mainly based on text search function. However, text information may not properly reflect visual content. That is why we cannot properly search image or video by only using text information. So that is why this motivates researchers to address extracting semantic or concept information from visual content. I believe many of you are working on that. But this is basically very difficult, mainly due to so-called semantic gap in multimedia content or multimedia content analysis. And so we need to bridge it, as you may know. Let me show you some example why text is not good enough. I once tried to search for images via Google image search function, and at that time keyword was people playing drums, and what I expected is to search for images where people are playing drums, of course. So, and the results are, as you can see, I could get those kind of results. So that can be okay, right? So people are playing drum like this, or even some people are playing traditional drums like this. So those are fine. But I could get quite strange results as well, like this. I can't explain why this was returned. I don't know why this is playing drum. Or I could obtain this image as well. I cannot explain. So text is not good enough, but current state-of-the-art image analysis direction is something like this. So currently, a typical approach is to train semantic classifier with training visual data. For instance, TrackVid project is one of that direction. Of course, many researchers are doing very well. However, the accuracy is still low, but improving every year. Okay. Right. So, ideally, such kind of method may want to collect all shots, for instance, representing visual concepts. One example is airplane flying. And this shows typical example of video shots showing airplane flying from TrackVid contents. So our TrackVid people's final goal is to collect these kind of shots showing airplane is flying from huge amount of video information, like several tens, thousands hours of video. However, I would like to ask you whether this can be good enough for our final purpose. I would like to argue that just collecting these kind of shots showing some specific visual concept is not good enough. This is like searching. For instance, we can think about text documents, and let's think about huge amount of text information, and we can specify one specific keywords to search for document, and this direction is to collect all documents including one specific keyword. Do you think it's good enough to search for text documents? I don't think so. But anyway, so still, researchers working in video image semantic classification cannot obtain this perfect result. And we need to first address this direction. However, this may not solve the final problem. Let me explain why. Let's think about the analogy with web search. So, well, of course, you know, web is a collection of web pages. Web pages are mainly based on text information. And web search can be accomplished by simple keyword matching. Of course, you can think about that. Some time ago, there are many search engines available. For instance, Lycos, InfoSeek, AltaVista. And they are mainly based on that kind of text or keyword matching. And as you can see, web is a collection of pages like this. And formally, search engines like these try to collect all documents which include a specified keywords or set of keywords, right? However, nowadays, those search engines will all disappear, right? Why? One is, of course, you may know, Google. Okay. So, well, however, those search engines just regard each page independently and did not use link information. However, web pages have links, of course, as you may know. And Google popped up, and it effectively utilizes link information, as you may know. So, as you can see, each pages formerly were treated independently, but there were links, as you can see, and Google PageRank algorithm effectively utilize the link information and try to estimate the weight of each link as well as page rank or weight of each page, and they effectively reorder or re-rank returned web pages, and that effectively reflect the contents of web page. So you see big difference. Utilization of link information, it was the key of the success of Google. So the key point of this talk is why not we use link information or link analysis for video or image search research. However, link was exist in web pages, but we don't have any link information in image or video, right? So question is how we can obtain links from, for instance, video archives or image information, and how we can use link information in video archives. That is the point. Okay. So those are example of link information, what we can think of. One is video copy or video near duplicates information. So video copy is basically a shot used multiple times in a couple of video programs. As you can see, there are 3 examples of shot which was used multiple times. For instance, this was taken from a shot of World Cup match where Japan won. This was used many times in Japan only, maybe. You didn't see this, maybe. And maybe you know this guy, and this kind of shot was used many times as well. And this is the nuclear plant of North Korea, and this was used many times in Japan as well. And I could see this shot in French or US or other TV broadcasting as well. So those kind of shots can be detected and might be used as a link information. Okay, or other type could be face information, because face is very important information source in video programs, news or. Okay, sorry. Let's restart. So we were here, right? So face information. So face is very important. On the other hand, research efforts of face is extremely improved. That is why we can detect faces as well as match. So we can use that. So we can detect face as well as track and match appearing in TV broadcast. So for instance, we can detect this face, and we can recognize this and this are the same person, or we can detect this, and we can recognize those two are the same. Then maybe we can use these two are linked and these two are linked as a, how to say, identifiable face information. Yet another type of link can be object detection and matching. This is getting more difficult though, but maybe we can detect specific object appearing here and this as the same object, or well, it could be very difficult, but we can identify that this car appears in this scene as well. Once we can do that, we can use that kind of information as a very strong link information. Final candidate could be semantic shot classification, like classifying shot into airplane flying or that kind of semantic concept information. One example could be those shots including airplane in the air, and those shots showing sports, and those shots including buildings, something like that. And we can regard those shots as somehow linked in terms of semantic similarity, and those shots as well. Maybe we can use those as rather dense link, because those links are rather rare, but maybe these kind of link can be a bit weaker than those. So those are examples of link information. And still, we can say, sorry, this, right. We have to think about the difference between TV archive and web information. If we think about broadcasted video, we can observe a couple of good properties of broadcast video information. One is, of course, TV broadcasting is very high quality compared to web information or video available on the web. Compared to those broadcast video by TV station could be very high quality. Basically, there is no false information or no fake affiliate blog, etc., etc. So we can rely on that. On the other hand, basically, we can think about a couple of TV stations. Some are in one country, some are in the other countries as well. But they are watching only one real world. Of course, you can think about that. And they may share the same point of interest, maybe. For instance, of course, we have many TV stations all over the world, but they may have similar interest to, for instance, World Cup soccer game now. Or if there is big problems, maybe they may focus on that problem as well. And all of these will be fed to viewers like us, right? So, and they may want to attract viewers' attention. They may somehow share the common interest. And basically, so if you think about this structure, TV broadcast could be very well structured, and we can use date information or time information or channel or even country information of TV channels, right? And if we think about each channel independently, we can observe some broadcast here might have semantic relation to the different TV program of the different TV channel. And that may also have relation to this program as well. And on the other hand, with the other topic, maybe all 5 channels may have the similar TV program. Then this topic might have a strong impact in maybe real world or something like that. And once we observe this kind of relation, we can get higher semantic information for each TV broadcast. Okay, this is one example. For instance, if we think about one channel, maybe specific shot might appear many times, and that can be the opening or jingle of specific TV program. This is not so interesting example. On the other hand, this kind of shot, this is North Korean nuclear plant shot. We can observe many shots appearing in TV, Japan TV programs, as well as US and French program as well. And this guy, this is former Prime Minister of Japan. This face might appear many times in Japanese TV programs, but maybe not in US or French TV program. And this guy appears many times in US TV program and Japan and so on. So we can observe this kind of link information. So this motivated us to use link information within TV broadcast video archives. All right, then let me explain a couple of our research activities, how to extract that kind of link information. And first of all, I'd like to explain about video copy detection research efforts and use that as a link extraction. So nowadays, video copy detection is quite aggressively researched topic nowadays. And essentially, video copies are very rare, as you can see. If your TV program is full of video copies, it's boring, right? So basically, video copies are very rare. And therefore, very accurate method is required, right? So if that method has small false alarm rate, if you think about, for instance, 0.1% error rate, false alarm rate. 0.1% normally is very low. However, positive match of video copies are very rare, and there are a bunch of non-copies there. Then even 0.1% error rate might cause full of false alarms, right? So you have to be careful about that. We need very accurate method. And unless applied to huge video archives, you can obtain nothing, right? If you apply your video copy detection method to only 1 hour of video, maybe you don't see interesting copies there. You have to apply that to hundreds or thousands of hours of video, otherwise you cannot see any interesting video copies there. So the method should be highly scalable, right? So that is why one direction is to achieve very scalable video copy detection method. So let me explain about that. So this is the basic process of our very scalable video copy detection. This is rather simple. First, think about given videos, both reference and queries. So idea is to, so we have database, which is reference video, and we may have queries. And question is to detect whether part of queries might appear in any part of reference videos. And normally, reference video could be very huge, several hundreds, thousands hours of video. And given query may have, for instance, piracy copy of video, for instance. And we want to detect part of that appeared in reference video. So to achieve this, what we do is to convert that into extract keyframe information from all videos and convert that into feature information and put that into our database. And basically, our feature information is based on point of interest information, means local information. And we use local descriptor, whatever will be fine, saved information, whatever. And we convert that into 2 parts. One is local descriptor, which is one difference from other research, which is not global, not local, which is combination local information. And we also use local association information and put both information into buckets. So basically, this is like a hash-based method. And we visit each bucket and get the possible copy out of that. And each bucket, we evaluate the similarity between reference frames and query frames. And finally, we get copy information. So let me go into detail. So first of all, as I mentioned, we use local information. So given this keyframe, we detect local point of interest points, like this point, or as you can see, this crossing points, or this, or maybe eye, or something like that. And we also obtain local descriptor, like shift or glow, or whatever can be fine. And we finally extract as a pair of information describing the local descriptor and position in image. So this is very standard. Then we convert that into local information. Let me explain that. To do that, first we quantize feature space into a couple of separated region. So in this example, I visualized one feature space into two-dimensional. But for instance, if you use Swift descriptor, this could be 128-dimensional. So be careful. But for visualization, I simply use two-dimensional. And in our method, we simply divide each axis into a couple of fragments. In this case, I decompose one dimension into 4 and one dimension into 4. And in actual situation, we decompose one dimension into 2. But for visualization, well, I use this. And let's think that each point may have corresponding location number. This can be 1, this can be 2, up to, sorry, this should come here. Okay, be careful, this should come here. So in this case, 16. And in actual situation, we use 10-dimensional feature space, and we decompose that into 2 for each axis. That is, in total, we have 2 powers to 10 cells. That is 1,024 cells, okay? So, but in this case, we have 16 cells. And one feature point, let's assume that one feature point might appear here. Then we can associate this point to number 2. Then what we do is to put 1 at this location, second information. As you can see, this has 16 bits binary information, okay? And we associate this location as this bit. On the other hand, if we observe those 5 points altogether, what we represent is like this, okay? So this corresponds to this second, and let's say this corresponds to 5 here, and this corresponds to 10 here, and this corresponds to 13 here. One thing we have to note is that even though we have 2 points here, we disregard the number of points. We just use whether there could be point exist or not, okay? So this is, in that case, this is not bag of words. This is rather a set of words representation. And by using this, we can convert each keyframe into this simple binary vector information. So this is our local description. So in our case, we, as I mentioned, we use 10-dimensional feature space. That is why each keyframe might be represented as a 1,024 bits information. Okay. So key property here is that we don't need clustering in this case because we use regular grid quantization. Okay. Then, all right. Let's think that we have those points detected from one keyframe. And not only local information, we use spatial association as well, because well, local information or even a bag of key points representation, it does not have any spatial information in there. And in order to incorporate spatial information, we use this kind of association information. Let's think about this point of interest. And what we do is to find 2 nearest neighbors from this point. And we use this triangle as an association. Okay, I will explain how we use this information in the next slide. And we also use 3rd and 4th nearest neighbors and 5th and 6th nearest neighbor. As such, we can extract a couple of triangles for each point of interest, right? And we can do that. We can do the same thing for the different point of interest, and we can compose those kind of triangles as well. Okay. as such, we detect 150 key points per keyframe, and we use up to 5 triplets or triangles per point of interest. There can be overlap each other and could be up to 750 triangles per keyframe. Okay, and how we use that is explained here. So given keyframe, we detect all key points and we can extract local descriptor as I explained. On the other hand, we can extract a couple of triplets, as I explained, that can be 600, what was that, 750 or 600, well, something like several hundreds triplets information. And for each triplets, for instance, we can think about these 3 points, and these 3 points appears here, here, here in feature space. And position can be 1, 3, 11, for instance. Then we compose corresponding buckets for those 3 triplets. And once we identify these buckets, we put this local descriptor into these buckets. This is what we do. So for each keyframe, we generate local descriptor, and that could be stored into several hundreds buckets. Okay. Okay, maybe we can skip that. And for instance, if we think about 3 triplets, this global descriptor might be stored into 3 buckets. But in reality, this can be several hundreds. And plus shape code information as well to further speed up the search. So what is shape code? Shape code is rather very simple. If we observe one triangle, we simply calculate ratio between longer edge and smaller edge, which is very simple. And in this case, for instance, shape code can be very close to 1. And in this case, maybe the ratio could be between this and could be 2.5, something like that. This roughly reflects the shape of each triangle. And finally, so as I explained, based on that method, we store all keyframes, both from database and reference, into buckets. Finally, then after we build all those buckets information, we visit each bucket and observe what kind of reference keyframes and what kind of database keyframes, reference and query keyframes were stored in each bucket. And once we identify reference and query frame information stored in there, in most cases, buckets are empty. Be careful. In most cases, buckets are empty. But once we detect reference and query, then we evaluate the similarity between local descriptor, right? So that is based on dice distance, which is very simple. And also, once that has the similarity, then we also think about the similarity, similarity in terms of shape code as well. Okay, so by using this, we can detect the matching keyframes. All right, so maybe we can skip this. So we can match keyframes, but afterwards we have to extend that to a sequence of frames. So we need to do some post-processing. Then finally, we can obtain a very scalable video copy detection method. And we actually implemented that for TrekBit 2009 campaign video copy detection task. And the result was here. So this means, so this corresponds to the accuracy. This direction corresponds to higher accurate method. And this is lower accurate method. And this corresponds to time information. This takes longer and this takes shorter. And ours is here, very high speed and very accurate, okay, as you can see. All right. And we also built a sample implementation based on that. We store video TV broadcast information in Japan, 7 channels, 7 weeks, in total 8,000 hours of video. And the system can accept any image as query and find matches in this video database. And this is the result. This image was obtained from web. And actually, this is the shot of commercial film. And this is a result of match. As you can see, this shot appears many times in different TV channels on different days. Of course, this is commercial film. And this is the shot of specific TV program. And our method can successfully identify that shot in the actual appearance of that program. And even, so this is very interesting result. This is the given query. And our method can identify this shot, and as you can see, our method can identify this logo in the video information. So our method can have some robustness to the background clutter and so on. Okay, right. So let's see. I have to be hurry a bit. Okay. So this is one.
20 minutes. You still have 20 minutes.
20 minutes. Okay. Thank you. Okay. So that was video copy detection, and now we that was based on local information, and that is why it has some robustness to background information and such. Now we restrict that situation more tightly, and we detect much faster video copy detection method. And based on that, we realized commercial film detection, right? So, we simply regard repeatedly occurring frame sequences in broadcast video with certain duration could be commercial film, right? By doing that, we can detect as well as identify commercial film very easily, as you can think. What is the benefit? Actually, if we detect commercial film, we can remove commercial film, or we can monitor commercial film. Maybe some company may have interest in this, or we can also do marketing research as well. Okay. So how we do that? So what we do is very simple. We decompose given video like this into frames. In this case, we don't use keyframe version. We use all frames. And we simply convert each frame into very simple binary signature. In our case, 32 bits, very small signature. And we regard frames sharing the same signature could be visually very similar, of course, right? And once we observe this frame sequence and convert that into binary signature, if this frame and this frame may share the same binary pattern, then we convert this, we group them to one frame groups, okay? And if these two and these four frames share the other binary signature, we compose another group. Okay, so in this case, we have two groups. One is this and this, the other is these and these. Then what we do is to convert each group into temporal occurrence pattern. So for this group, we convert that into this temporal binary sequence where this frame occurred here and this frame occurred here. And for this group, we convert that into this temporal occurrence pattern where 2 frames occurred here and 4 frames occurred here. As such, we can convert each frame groups into this binary temporal sequence. And once we observe commercial films appearing, specific commercial film appearing twice in our video archives, maybe we can observe this kind of temporal occurrence pattern. For instance, first part might occur here, and the similar occurrence might appear here, right? Because, well, we can assume that one commercial film here and the other commercial film here, and those are identical, okay? And as such, the second part might appear here and here, third part here and here, right? Then, if we can properly merge these into this, like this, then we can identify that one specific commercial appear here and here. And as you can see, if you think about raising edge, for instance, this raising edge and this raising edge may have this certain temporal offset, and this may have very similar temporal offset, right? Then, based on that, maybe we can obtain similarity between each of these pairs of temporal occurrence pattern, right? So by doing that, so once we convert everything into groups and compute temporal occurrence pattern, we can define similarity between temporal occurrence patterns, and we simply apply agglomerative clustering method. Okay. Of course, we can think about temporal offset as well, but once we properly define similarity, we can simply do agglomerative clustering. And this is the actual result. We applied a method to, in this case, 1 hour of TV program. And once we set certain threshold like this, we can obtain 8 clusters. Okay, and actually, we also built our ground truth, and we compute confusion matrix like this. And actually, those 7 clusters corresponds to 7 commercial films, 7 types of commercial film. And this large cluster corresponds to the actual program information. So our method can successfully identify commercial film as well as detect commercial films as well as identify. And we applied the similar technique to 1-month video archives, and those are result of sample of detected, identified commercial films. And by doing that, we can even plot the distribution of specific commercial film, and this corresponds to dates, and this corresponds to hours. And this one is the commercial of specific bread information, and you can see this commercial film might appear in almost any time from around morning 6 until 10 p.m., right? So this commercial film for ordinary people or housewives or any people. And this one is a commercial film of specific movie, and this is mainly for adult people. And as you can see, commercial film appears only after midnight, right? So we can observe that kind of thing as well. Okay, let's see. Let me simply go through. So that one, that I explained about 2 methods, and those are basically detecting this very similar video shots. But let me show you 2. Can you see? So those shots are taking the same scene. Can you see? Same person are saying something, but you can see those 2 are taking the same scene, right? But of course, you can see these 2 are taken from the different viewpoint. Of course, we can identify those 2 are taking the same scene, but it's very difficult for computer to identify, right? Do you agree? But different camera, yeah, even different camera, of course. So camera parameters are different, right? Everything is different. But can you see some specific thing appeared there? Eye blinking could be very interesting. Flashes. So actually, what we use was flashlight in this case, right? So let me show you again. So yeah, flashlight, yeah. So of course, even though those 2 are taken from the different viewpoint, different cameras, flashlight, they, yes.
Actually, I think the
look at the green pen on the right, on the left images,
Yeah.
is on the left. And if you look at the right sequence, the green pen is on the right.
This one?
No, the whiteboard, I think. There's a pen.
Ah, this one.
Yeah. Look at it's just different.
But this appeared here, maybe? I don't know. Or was
might be
occluded
the
or
same.
Could be the difference.
You might need have another thing on the right hand side that you cannot see on the left video.
Maybe there is
yeah, due to occlusion or yeah. But I'm very sure. Well, if you hear the audio, I'm very sure that those two are the same scene. Yeah. Okay. Anyway. Oops. Oh. Right. So, what we did is very simple. We decompose given video into shots, and we detect flashlight and convert that into this kind of binary pattern. Each bit corresponds to frame, and once there is no flash, that be corresponded to 0. And once you can observe flashlight, that we assign 1. Then we can observe this kind of binary sequence, and we simply match them. Maybe we skip everything there. Right. But if you think about TV broadcast, in some cases, audio was removed and replaced by anchor person's speech. In that case, we cannot use audio information, unfortunately. Of course, we can think about audio information, and we can use multimodal information. All right. Okay. So this is example. So we already observed this, and our method could detect this pair and this pair as well. And one interesting pair could be this. These two shots were taking one baseball player who started to play in the US, and one camera focused on his number. The other camera focused on his face. Even in that case, our method could detect. This was impossible by using any fine computer vision method because there are no overlap. But if we use a flashlight, we could detect this. But of course, our method could detect only our method can apply only to shots with flashlight. So that is one drawback. And we further extend that. Okay, let me. So this is very good view graph of near duplicate. So this kind of near duplicates can be detected by our former method, right? And those two looks very similar, but definitely they are the different shot. He's a Japanese governmental spokesman, and he is speaking about the different topic on the different days. So in that sense, these two are totally different, but looks very similar, right? So what we are interested in is, yes, this kind of thing. Shots taking the same thing, but from the different viewpoint. And unfortunately, in this case, as you can see, there is no flashlights, right? Then what we can do? So one is eye blinking, of course, but what we do was, yep. Okay, we can skip this as well. So what we do is, so let's consider that this and this corresponds to different shots. And what we do is to detect feature points and obtain trajectory of each of these points, okay? Then we can match each of these trajectories one by one, taking into account the shape of trajectory, and we can define similarity between these two shots. So this is what we do. And to do that, all right, we can skip. Right, so each line, let's assume that each line corresponds to one trajectory. So we need to convert three-dimensional trajectory pattern into this one-dimensional value. And in doing that, we use inconsistency, which is invented by Michel Irani. As you, well, that paper was awarded by, I see CVPR, I guess, 2006, might be. So in that sense, it's more or less very well-known methods, and we use that, and we can convert each trajectory into this one-dimensional information. And what we did is to detect quick motion change point like this, and regard each trajectory as this kind of binary information. And we apply similar technique to flashlight-based method for each trajectory. So this is what we did. So this is very simple. Maybe we can skip these. Okay. Right. So then our method could detect those kind of shots, kind of near duplicate, but taken from the different viewpoint, as you can see. Okay. But our method could not detect those pairs. In this case, perhaps, how to say, video camera direction is too different. One is taking very close to this guy's frontal location, and this guy taking the shot from side. Then maybe motion trajectory may have different pattern. And also, in this case, if there is so many caption information, video caption information, as you know, interest points might be absorbed onto those kind of highly textured region, and very few points might be tracking the actual face information and so on. And this shot is very interesting. So he is a Japanese emperor, and on one day, actually his birthday, he made speech, I guess 2 or 3 times. And one shot is taking his speech in the morning, the other is in the afternoon. And interestingly, he spoke exactly the same speech at exactly the same speed. That is why our method could detect. But those two are the totally different thing. Anyway. All right, so those are examples of video copy detection method. And maybe I would like to explain how we can use that to mine or that kind of information. So those are examples of video copies which can be observed in multi-channel TV news information. And idea is to use that link information to re-rank a given news story, given search query. So think about search query given in text information. And we have a news video archive there. Then we can retrieve a couple of news stories. But if we use only text information, that rank cannot be very reliable. And then we use near duplicate information to re-rank that given shot into more user-friendly way. Okay, so we first decompose given news video into stories using any kind of story boundary detection method. Then, if you think about one query, so if you think about multiple TV programs, even on different channels, we can detect those stories as a relevant stories. Then what we do is to detect, to identify whether, for instance, given these two stories may share video copies or not. As such, we can detect all those links, and then we forget about all the stories not sharing any video copies, and we detect those kind of groups having all linked stories. And we select the largest group and use this only as a relevance feedback information. And then we research all the stories again and re-rank. And actually, right. So this is the result. Right, so this is our method, and all those are baseline method based on text-based relevance feedback method. And compared to these, our method achieved higher accuracy, of course, which is much higher than the original method. All right, and maybe final example. So that one is based on text and video copy detection result. And this one is visual information only. And idea here is to, so given very huge video archive, more than 1 year video archive, and what we would like to do is to identify very informative shots from that huge video archive. And our assumption is that shot expressing each very impressive event might be used many times. For instance, as you can see, this shot might used many times, and this guy, this is North Korean leader, and this is nuclear plant of North Korea. Those kind of shots might be used many times. And the others are related to Japanese domestic news, but so these two at that time fighting each other, and those shots were used many times. And finally, this guy was arrested by a scandal, and this was used many times as well, and so on. So idea is to identify all these video copies in huge video archive and use that link information to identify which shot is more impressive in specific time. All right, so we use much simpler video copy detection method, and once we do that, each shot might have specific temporal occurrence pattern. For instance, this shot, this is a signboard of police department in Japan. This was used here, 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 here. So this is around 1.5 years, very long, and this was used so diversely, as you can see, because, so this is signboard of police department. This was used to make report of, for instance, white paper report of made by police department. Of course, this was used. Or this also was used to report about a scandal appeared here. Those two are totally different story, but used many times. That is why this was used in totally different time. On the other hand, this one used only here, where after 2001 September up to October, and this as well. And once we detect all these, and we can observe that kind of temporal information, for instance, we can detect those shots appear having this kind of distribution, and we can identify those as a related to hot topics, or those might correspond to very rare shots. And those, for instance, this happen again, signboard of police department, those are used simply for symbolic purpose. All right, and we can also use face information, but maybe we can skip that. All right, so this is the last slide. So finally, our idea is to extract video copy information or face identification information, object identification information as a latent link information observed in video archives. And we would like to use that to further analyze the video information as well. So to do that, maybe we can go to those kind of possible direction. Maybe one is we can observe video rhetorical structure, or maybe we can think about to use that to enhance accuracy or enhance quality of semantic analysis, or maybe we can obtain film grammar, or we can automatically generate short person object recognition model, right? Or maybe we can compare cultural difference between videos of different countries, Japan and France as well, and categorize shots, programs, channels, and classify videos into cultural categories, countries, or survey person, object level, audience, rating, and so on. Okay, maybe we can go to different possible directions. Okay, thank you very much. Sorry for the technical problems, and thank you very much.
Thank you very much. So we can take time for a couple of questions.
I have a question. You showed very impressive work, but on commercial detection. And in commercial detection, what we often have is just a sort of logos and, let's say, more static scenes. And what about thrillers with a strong emotion? A lot of characteristic points will be occluded. And what is the robustness of your method in this case?
If we think about our commercial film detection method, here, well, if we think about local feature point based matching using only keyframes, so the situation where you explained could be suffered from, yeah. But if we use this method, we use all frame information. Then, even though there is strong motion, our method can handle that properly. No problem. Thank you very much. Very good points.
I have just a question about the keyframe search. When you group the region of interest based on KMN scheme, I just ask why you choose K value on 2, not 1 or 3 or any other value. Why we don't group the 4 nearest neighbor instead of the 2?
Actually, we use 2 nearest neighbors each and compose triangle. Of course, we can use 1 nearest neighbor, right? 1 nearest neighbor for given this point of interest, we can use only 1 nearest neighbor. But in that case, we cannot obtain rich shape information. We can obtain, of course, distance, but distance only. But that may, well, that may suffer from scale change or those kind of things. So that is why instead we use 2 points to compose triangle. Then we can compute shape information, right? Of course, we would like to obtain many points, for instance, corresponding to this hippopotamus, for instance, or object of interest. But it's very difficult which points corresponds to object of interest, right? So this is one of compromise. Yeah, not so many points, but just 1 is too few. So we selected 2 to compose, yeah, triangle. But maybe we may want to use more intelligent method to select points, and we would like to obtain the actual points corresponding to the actual object. But that is still difficult.
Yeah, on the same topic, I didn't really understand how you got so few buckets, because if you take all possible triangles and you say you code on, I think, 1024 bits,
yes.
So it makes all, if you take all words with 3 bits,
yes.
It makes a lot more than that. So did you do some sort of clustering afterwards on the triangle?
We simply restrict the number of triangles per each point. So for each point, we generate only 5 triangles per each point, right? So that
at the end, I understood you have these buckets,
yes,
which correspond to some triangles.
So each bucket corresponds to triangle, yes.
But you build the buckets for the entire database?
Right.
So
it's huge.
There are many triangles?
1,000 times 1,000 times 1,000. Very sparse. Very, very sparse. Yes. So, well, we don't physically compose each packet because most of the packets are empty, right? So instead we use hash-like function. We realize only packets having points in there. Did this answer the question? So this is, yes, as you mentioned. So there are huge variation of buckets, 1,000 times 1,000 times 1,000, but most are empty. Maybe we can discuss later.
I may have one final question.
Yeah, sure.
You mentioned that this process needs a huge amount of data in order to be usable.
Yes.
And huge amount of data means huge amount of resources, which is very expensive. So do you think that in the future the hardware will be cheap enough so that a lot of people can afford this, or that it will be a kind of only a few companies like Google which have a kind of monopoly of this type of analysis and type of usage?
Right. Very interesting question. Let's see. I showed example using Japanese TV programs, and we have a system. We built system which record all TV program in Japan, and we started this project since 2001. And at the time, I tried to buy 50 terabyte disk array, which is good enough to store 1 year of all Japanese TV program, and it cost me, let's see, how much? 5,000 million yen, so 50 million euro. 50 million euro, is it expensive? Oh, probably not? Oh.
But at least you could afford it. And the next
No,
year,
no,
could you
no,
afford it?
I couldn't. Yes, 50 million euro for sure.
Okay.
At the time, right? 10 years ago, right? But now I could buy it at, well, here maybe 20,000 euro or something like that. Yeah. So in that sense, well, prices keep going lower very rapidly. However, yeah, if you want to store all the broadcast in all over the world, maybe it's getting very difficult. And well, I don't know. I don't like monopoly, of course, but well, very good question. So to some extent, this can be available in each of house even, but good question, very good question, and
Okay,
I have
so
no.
it still needs more thinking to see how this has a real impact on everyday life.
Yes,
Okay.
yes, exactly.
Okay. Well, maybe National Archive can kind of produce this type of material and exchange it among several countries so that everything is available to the public. And,
yeah, I think so. Yes.
Okay. Thank you very much.